In the previous lesson, we talked a little bit about how to reduce and get it in triangular form. So this is going to formalize this a little bit. So we first need to make sure we're on the same page with what we're talking about. When I say a non-zero row or column, non-zero just means that one of them has to be not zero. So you could have some zeros, but as long as they're not all zeros, then it's a non-zero row or non-zero column. And the leading entry in a row refers to, as you're reading from left to right, it's the first non-zero entry. And a rectangular matrix is in echelon form. I often call it row echelon form, or REF, because that's the command that's in your calculator, if it has these properties. So any all zero row has to be at the bottom. The leading entry of the row has to kind of go from left to right, because it's kind of diagonal as you go down. So it moves to the right as you move down. All entries in a column below a leading entry has to be zero. And then to simplify more, it's reduced row echelon form. Again, I usually use the reduced row echelon form because this RREF is what's the function in your calculator, is all those three things we just talked about. And the leading entry is always a 1. And above every leading one, there needs to be zeros. So let's look at these 8 examples and see which are in row echelon form, which are in reduced row echelon form, or neither. So looking at this first one, I'm going to think about, are there any zero rows? If there's any row that contains all zeros, it needs to be at the bottom. Okay, here's a zero row. It is not at the bottom, so this cannot qualify for either one. The second one, there are no zero rows, so that's good. My first non-zero is in a kind of diagonal. Goes, every one you go to the right as you go down. So that's good. All entries in the column below are zeros, so because these are the zeros. This is in row echelon form. Let's check to see if it's in reduced row echelon form. Are all the leading entries 1? No, because I have a 3. So this is just row echelon form. All right, looking at the next one, I have a 1, a 1, and a 1. So those are my those are my leading entries of each row. There are no rows of all zeros. And all the ones below all the ones below my leading entries are zeros. That's good. So I know I'm in row echelon form. My leading entries are 1, and then above each leading one, I have zeros. So this is in reduced row echelon form. The next one, I have a row of all zeros, is at the bottom, so check. And then I'm going to find my leading entry. So there's leading entries. Below them, I need to be zeros. So below them, I am 0. Good. So that is in row echelon form. If I had zeros up here, I'd be reduced, but I'm not. So it's just row echelon form. Ask you to pause here and try to do the next 4. So when we're determining whether or not it was in reduced row echelon form or row echelon form, we looked at the first non-zero entry in each row. That is called the pivot position. And then there's the pivot column, which is the column that the pivot's in. And that value is called the pivot. So if it's reduced row echelon form, it's always going to be a 1. So we often talk about a leading 1 is the pivot. So again, just some terminology. And then we have this row echelon or row reduction algorithm. And I'm just going to talk through it as I go through an example. So kind of the first thing you want to do is make your first pivot a 1. Well, it already is. So, great. The next thing I want to do is 0 out below it. So I want to make this 2 a 0 using elementary row operations. So I'm going to say row 2 is row 2 minus 2 row 1. So 2 minus 2 is 0. That's the whole reason for creating that elementary operation. And then 7 minus 8 is negative 1. 0 minus 0 is 0. 10 minus 14 is negative 4. Now, the next thing to do would be to create your next leading 1. So I need this to be a 1. So I'm going to multiply row 2. So row 2 is negative row 2. So just multiply by negative 1. So 1, 4, 0, 7, 0, 1, 0, 4. So I have my 2 pivots. I can only have 2 pivots if I have 2 rows. The next thing is to 0 out above any leading 1s. So again, the first thing was to 0 out below the leading 1s. Now, when you get all your leading 1s, I'm going to 0 out above them. So my row 1 needs to be row 1 minus 4 row 2. So 1 minus 0 is 1. 4 minus 4 is 0. 0 minus 0 is 0. 7 minus 16, negative 9. And then I still have 0, 1, 0, 4. So one of the reasons we like to get it in this form is once you have it in the reduced row echelon form, you can read the solution off of it. Because what this first row means is that x1 equals negative 9. Because remember, we have this augmented system, and it means that x2 equals 4. It also tells you that x3 can be anything. So I'm going to follow the same algorithm for this second one. I need my first entry to be a 1. It is. I want my 3 and my 5 to be zeros. So I'm going to leave my first row the same. And row 2 is going to be row 2 minus 3 row 1. And row 3 is going to be row 3 minus 5 row 1. So 3 minus 3 is 0. 5 minus 9 is negative 4. 7 minus 15 is negative 8. 9 minus 21 is negative 12. And then the next row, I have 5 minus 5 is 0. 7 minus 15 is negative 8. 9 minus 25 is negative 16. And then 1 minus 35 is negative 34. So next thing I'm going to do is I'm going to make this negative 4 a 1 by saying row 2 equals row 2 times negative 1/4. So 1, 3, 5, 7, 0, 1, 2, 3. 0, negative 8, negative 16, negative 34. Now I need to make the negative 8 a 0. So I'm going to say row 3 equals row 3 plus 8 row 2. So I'm using row 2 because I want to use the pivot column. So negative 8 plus 8 is 0. Negative 16 plus 16 is 0. Negative 34, negative 34 plus 24 is negative 10. So if I were to keep going to get reduced row echelon form, my next pivot would be this negative 10. So I want to make that a 1. So I'm going to say row 3 equals row 3 times negative 1/10. So that is, right now, that is in row echelon form. So now I'm going to work backwards, and I'm going to use the pivot right here to zero out above it. So to zero out above that, I'm going to say row 1 equals row 1 minus 7 row 3, and row 2 is row 2 minus 3 row 2. Looking at row 2, I have that's 0, and then 1 minus 0 is 1, 2 minus 0 is 2, 3 minus 3 is 0. And looking at row 1 minus 0 is 1, 3 minus 0 is 3, 5 minus 0 is 5, and then 7 minus 7 is 0. And now I'm going to zero out above the other leading ones. So I'm going to get rid of that 3. So I'm going to say row 1 equals row 1 minus 3 row 2. 1 minus 0 is 1. 3 minus 3 is 0. 5 minus 6 is negative 1. And then 0 minus 0 is 0. And the others stay the same. So now this is in reduced row echelon form because I have my 3 pivots and I have my zeros above and below my pivots. I also just want to point out that I would have not gone through all of this if I was actually solving this equation. Because this line, that row, means 0x plus 0y plus 0z equals 1, and that's not possible. So that tells me there's no solution. But I could have seen that right when I got to this point, because that tells me that 0 equals negative 10, which is just not possible. Now we're going to use row reduction to look at a different type of solution. So when you have 2 equations and 3 unknowns, or if you have fewer equations than you have unknowns, you will often get infinitely many solutions. And you have what we call free variables and basic variables. And we're going to work on writing the general solution to something like this. So first thing I want to do is just write the augmented matrix that corresponds to this. And I'm going to say, you should practice doing this. I am skipping a lot of steps. This is in reduced echelon form. All right, so once you get it in this reduced echelon form, how do you write the solution? So I'm going to look for where the column, so this is my x1, my x2, my x3. My x2 column has no pivot. So that's a free variable. So I'm going to say x2 is free. In other words, it can be anything. I'm going to write the other 2 equations down. So row 1 tells me that x1 minus 2x2 equals 2. And the second row tells me that x3 equals negative 2. So if I were to write a generic solution, my x3 is negative 2, my x2 is free. In other words, it can be anything, so I'm going to leave it as x2. And then to write my x1, I'm going to solve for x1, and it's 2 plus 2x2. So that's the generic solution that represents all of them, where x2 is any real number. You can think of it just an example. If I let x2 equal 1, then I would get negative 2 for my x3, 1 is x2, and then 4 would be my x1 in this case. So that's an example of one solution. So this is one solution. And this represents all solution. So we're going to work on this existence and uniqueness theorem the entire semester. So just keep that in mind, we're going to build on this. So a linear system is inconsistent. Remember, inconsistent means that it has no solution if and only if you have this 0b. So remember, that's like 0x1 plus 0x2 plus dot 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 plus 0xn equals b. So you can't have 0 equals a number. As long as b is not 0, that means there's no solution. If a linear system is consistent, meaning it has a solution, then if it does not have a free variable, then it has a unique solution. If it has a free variable, then it has infinitely many solutions. So let's suppose we have a 3 by 5 coefficient matrix. So I'm just going to put kind of stars into the entries. So 3 rows, 5 columns. And because it's coefficient, I would still have some b's over there, if you want to write it that way. We're told it has 3 pivots, so maybe there's a pivot, a pivot, a pivot. Is the system consistent? So because I have a pivot in each row, I know that it's consistent, and because I have these two would be free variables. So my x, in this case, my x4 and my x5 are free. That tells me there's infinitely many solutions.